Hello, everybody, and welcome to our very last chapter of AP Calculus. We are learning about area between two curves today, and then we'll be learning about some applications of that in the next next week and a half. Before we start on this, I want to kind of remind you how we ended up finding area under a curve. So just bear with me here. You might, if you want to write this down, that's great. You might have to think back to, just get a separate sheet of paper or something. But let's think back to when we were given a curve like this, and we were asked basically to find the area. And the way we started doing this was we started by drawing rectangles, right? We started drawing some rectangles and basically finding the area of these rectangles, right? And we had like left Riemann sums and right, these left rectangles and right rectangles, and basically what we did was we added all these rectangles up, right? We added the area of each rectangle up, and it gave us an approximation for the area, right? And the approximation wasn't always that great, but it gave us some decent approximation. And so one thing that we did before is we, like, the widths of these rectangle, we ended up making them like consistent. So like it'd be like delta x, which was like the width of the rectangle, and then based on whether we chose what endpoint we chose or whatever, the height of the rectangle was basically the x coordinate, right? So there's some f of x, like I, where I just keeps track of which x coordinate we're at. And so like the area of maybe rectangle 1 would be f of x1 times delta x, because that would be the this guy was the height, and then this delta x was the width. And so that's how we'd find the area of that first one, and we add it to the second one, the third one, the fourth one. And you can kind of see over here on the left we have a demonstration of that, except these are using so we'd use the left endpoints like that, right? And you can see it's a pretty bad estimate. So we also talked about this, where we go from sorry, this should be let's put a K there for this time. And so basically what this was it was the sum, right? This symbol here, this means sum. So it's basically just a shorter way of writing this whole thing that we had up here, of adding all those rectangles together. And we're just like, okay, well, the area is approximately equal to the sum of the height. Again, this is the height times the base. And then what we did was like, oh, well, and come over here to this demonstration here. We're like, well, what if we increase the number of rectangles, right? Won't it give us a better estimation of the area, right? So we made the rectangles be smaller and smaller and smaller, right? And it, like, basically the idea is if you take an infinite amount of rectangles, then you'll have the exact area. So what we did, I'm gonna write this over here, is we took the limit as n goes to infinity. And remember, n is like it's the number of rectangles, right? This n up here is the number of rectangles. We're taking the limit as n goes to infinity of this sum, right? It's basically saying we're going to add the areas of an infinite amount of rectangles together. And there's a really awesome proof for this, but basically what we said was, well, this is going to be equal to, it's not an approximation anymore, but it's going to be equal to the exact area. And what it also ended up being is, remember how we were talking about this as a sum? Well, it's the, so we could use the letter S. It's the sum of f of x, and then this, delta x just is like we just had it become dx, right? Delta x dx. And then the limits are just from a to b, depending on the a and the b are the left bound and the right bound, right? And so basically what we discovered, or what we found out, was that the area of any curve of f of x between f of x and the x-axis can be found exactly by using the integral, right? So just wanted to touch on that. So let's go down to here, right? And the first three little problems on here, just asking us to find the area of the shaded region, or write an expression that would give the area. And so sometimes it's helpful to think like, well, we could be drawing little rectangles here, and then that would help us find the area. But really the area is simply the integral from a to b of f of x dx, right? We'd add infinite amount of rectangles together, but it would become this integral, and this integral would tell us the area under that curve. And likewise for g of x, right? We would find, the area of this is going to be the integral from a to b of g of x. Right, so this shouldn't be anything new. Like we've talked about this, the area between a curve and the x-axis is basically the integral over the interval, right? And so here's the new part, right? Well, how do I find this region here, right? Like, so it's the region between f of x and g of x. Might as well think about it a second. Like you probably figure this out by yourself, right? But if I start drawing what the rectangles I need to use here, notice how they look like this, right? So the areas of these, like if I was trying to find the height of this rectangle, right? It wouldn't be this entire height, right? That entire height would be f of x. It's basically that big height, but then we don't want this little bottom piece on here, right? So basically the area of this one would simply be still from a to b, right? The integral from a to b of, to find that red piece on this is simply f of x minus g of x, right? So is the top function minus the bottom function, and that will tell me the area of the region between f of x and g of x, right? And so basically that's what this says here, right? The area of a region between two curves. We're saying that they're like, so there's some conditions. We don't have to worry about this too much, but they must be continuous. G of x must be less than f of x, which just means g of x is below f of x. And then if that's true, then the region bounded by the graphs between the vertical lines x and a, x equals a and x equals b, which is just those left and right hand limits, is equal to the integral from a to b of f of x minus g of x. And there's a slightly more helpful way to think about this, right? The area is going to be from, I'm going to go and write x equals a, x equals b, so you know that those are x coordinates, and it's basically just going to be the top function minus the bottom function, right? So whatever's on top minus whatever's on bottom, and then you just have to integrate, right? Sometimes you're allowed a calculator, sometimes you're not. We're going to go through like different examples with and without calculators, and then there's different cases and stuff like that. So let's go ahead and try this out, right? It's usually very helpful to have a little graph because you need to know which one's on top and which one's on bottom, right? So I recommend having a little graph as you start, right? So here's our two functions. I'm going to do some examples. In example 1, we want to find the area of the region between y equals x plus 2 and y equals negative 1/2 x plus 1. So x plus 2 is a line that starts at 2 and has a slope of 1, right? So it's going to look like this. This is that. And y equals negative 1/2 x plus 1 starts at 1 and has a slope of negative 1/2. So this one looks like this. And we want to know from x equals 1 to x equals 2. So basically we only care from 1 to 3. So we only care about from there to there. So the region we're interested in is right here. Right, and you might think, oh, it's, well, the little bit's below the x-axis, so it's going to mess it up, but it's not, because you're going to end up subtracting it anyway. So, don't worry that it's below the x-axis. It doesn't actually matter. And so, to find this area, basically, we're going to do the integral from top to bottom. So, the area here is going to be the integral from a to b. In this case, a is 1, right? That's the first x value. B is 3. Of the top function, which in this case is x plus 2, and then we're going to subtract the bottom function, which is negative 1/2 x plus 1. Right, and we need to integrate that to find the area. So we're going to do this one by hand because it's, it's a polynomial. It should be fairly easy. So let's go ahead and just clean up the inside first, right? It's going to be, otherwise it's, way harder than it has to be. Let's distribute that negative to give us 1/2 x minus 1. And then let's go ahead and combine some like terms. X plus 1/2 is going to give us 3/2 x. 2 minus 1 is going to give us 1. And now we're ready to integrate. So let's go ahead and integrate. The exponent here is 1, so we're going to add 1, divide by what we get. So this is going to be 3x squared over 2. We write it like this, times 2, right? That's dividing by the number that we got, plus the integral, the antiderivative of 1 is x, right? Think about if I take the derivative of x, I get 1. And then we're going to hold on to our limits of integration over here. We're going from 1 to 3. Right, so basically, now we just need to plug in our limits. That's where we're going to plug in 3, and then we're going to subtract what we get when we plug in 1. Right, so here we're plugging in 3, here we're plugging in 1, and let's go ahead and do this. This is going to be 9/27 over 4 plus 3 minus, make sure you keep some parentheses here, this is going to be 3/4 plus 1. We need to add these things. So 27 over 4 plus 3 is the same thing as 12/4. So this is going to be 39/4 minus 3/4 plus 1 is the same thing as 3/4 plus 4/4, which is going to be 7/4. And then 39 minus 7/4 is 32 over 4, which equals 8. Right? So it's kind of nice that that's a whole number, but the area between those two curves from 1 to 3 is 8 units squared, right? We don't have a unit on there, but 8 units squared. All right, let's do another example and look at some different cases, right? This is slightly different here. So again, a graph is helpful. We want to know the area enclosed between those. I'm going to make this a really big scale because I already know what's going to happen here. So we're going to graph y equals x, right? That looks like this. This is y equals x. And we're going to graph y equals x squared. Y equals x squared actually looks like this. And so we're trying to find, if you're not convinced about this, you can graph it on your calculator if you want, but you should know that this is generally what it looks like. We're going to look like this. And that's the area we're trying to find, right? So let's go and start writing the integral, right? This is going to be the integral of top minus bottom. So which one's on top, right? Notice that the line is on top, so it's going to be x minus, which one's on bottom? Well, x squared. And notice I've left something off here, right? We don't know what our limits of integration should be yet. We're like, what are my limits of integration? It didn't say from where to where, right? Like it didn't give me the A and the B. So basically what we need to know here is these 2 points, which are the points of intersection, right? And they look kind of obvious, but you need to make sure you actually can get them, right? So the way we actually get them is to find the points of intersection. We need to set these two functions equal to each other, right? Because the points of intersection are where the functions are equal. So I'm going to take the first function, x, and I'm going to set it equal to x squared, right? And you can logically think this one through, like when does x equal x squared? When does a number equal itself squared? Or you can go ahead and subtract x from both sides. So you're going to get 0 equals x squared minus x. and then we're going to factor the left-hand side. Sorry, we're going to factor the right-hand side, and the two solutions we'll get is x equals 0 and x equals 1. Right, those are the 2 points of intersection, so those would be our limits of integration up here. We're going to go from 0 to 1 because those are the points of intersection. It's 0, 0, and 0, sorry, and 1, 1, but we're using the x coordinate. Right, so now we can go and integrate this. So it's going to be, let's do this in a different color. It's going to be, I'm integrating now, right? So the integral of x is x squared over 2 minus x to the third over 3. And we're going from 0 to 1, which means we plug in 1 first. So we're going to get, I'm going to go ahead and erase this stuff so it's out of our way. We're going to end up with 1/2 minus 1/3 minus, when you plug in 0, you get 0 halves minus 0 thirds, which is 0. So we just have to do 1/2 minus 1/3, which ends up being, oh, we're subtracting. So 1/2 is the same thing as 3/6, and 1/3 is the same thing as 2/6. So we need to do 3/2 minus, when you do this, you get 1/6 units squared. All right. So again, the new thing here is to find the limits. You had to find the points of intersection, right? And this, in example 3, something similar is going to be happening, but it's going to be a little bit tougher to find those points of intersection, or a little bit different. Again, let's go and just start by setting up the integral. Right? We're going to write integral. We don't know a and b yet, but we do know we want to do, I'm just going to write this one out. We want to do top minus bottom. Right? So we're going to do the integral of the top one in this case is 2 minus x squared. And we're going to subtract the bottom, which is x. Notice I'm putting parentheses. That just makes sure I don't forget that the negative distributes in there somehow. And so before we continue here, we need to find the points of intersection, right? Again, all it involves is setting these two functions equal to each other. So I'm going to set x equal to 2 minus x squared. Get this one on the other side. We're subtracting x on both sides. So it's going to be 2 minus x squared minus x. I'm just subtracting x on both sides. I'm going to rearrange this so it's a little bit easier to work with, right? I can just rearrange those terms however I want. Also, I don't like dealing with negatives, so I'm just going to multiply both, or divide both sides of this equation by -1, because I don't like it when the x squared is negative. That's going to give me this. So now I need to factor. This is going to be x and x. I got to get a -2 there, which means this got to be, one of them's got to be 2, one of them's got to be 1. The 2 has to be the positive one, and this has to be negative. And so the two solutions are x equals 1 and x equals -2. Right? You can see here, this is going to be when x equals -2, and this one right here is going to be when x equals 1. We could find the y coordinate. We don't really need to. Basically, what it tells me is that's that's -2 and that's 1. How did I know to put the -2 on the bottom? Well, the smaller one should go on the bottom, right? It should always be like, this should be the left endpoint and this should be the right endpoint, right? It should go from left to right. So the further left one goes on the bottom. Okay, and now we're ready to go and integrate this. The integral of 2 is 2x. The integral of x squared is x to the third over 3. The integral of -x is x squared over 2. And we're going from -2 to 1. Right, so we're going to start by plugging in 1. It's going to be 2 minus 1/3 minus 1/2. And then subtracting, what happens when we plug in -2? This is going to become -4. -2 cubed is 8, -8. So this is going to be positive 8/3. -2 squared is 4. So this is going to be -4/2, which is 4/2 is the same, or sorry, 4/2 is the same as 2. Right, and let's go ahead and distribute that. Let's do a couple of things. let's get all of these with a common denominator. So this is going to be, the common denominator is going to be 6. This is going to be 12 sixths minus 2 sixths minus 3 sixths. This is going to be plus 4 minus 8 thirds plus 2. Combine all these together, we're going to get 14, or we're going to get 10. This should be a 6, 7 sixths. That's this 4 combined with that 2 is 6. So that's converting to sixth is 36 sixths minus 16 sixths, right? 8 thirds is 16 sixths. And so we have this, which is 36 minus 16 is 20 plus 7. We're going to get 27 over 6 units squared there. And then I guess that simplifies. If we need to, we can simplify by 3, which give us 9 halves, right? Same thing as 9 halves, or 4.5. Okay, so that's that example. Let's do a couple more examples just to see some different types of things that happen and maybe relearn our unit circle here. So here it's saying the sine and cosine curves. So it's telling us sine and cosine are graphed below. They intersect an infinite amount of times, right? Because they're oscillating and they're off a little bit, so they intersect a bunch of times. Here's one such example. They're bounding regions of equal area. Each time they intersect, they bound a region of equal area. We want to find the area of one of those regions. So basically, we're just being asked to find the area of this region, right? So there's a couple things we got to do. One, we got to figure out, it's got to be top minus bottom, right? So don't forget, it's got to be top minus bottom. So which one's on top here? They didn't tell us which one sine was and which one's cosine was, right? So you got to kind of remember, like, which of these functions starts at 1 and which of these functions starts at 0. We should know that sine of 0 is 0, so this is sine, and this one here, cosine of 0 is 1, so this one's cosine. So our integral should be sine x minus cosine x, because in the interval we're trying to find, sine x is on top. And the next thing we need to find is, what are my limits of integration, right? What are those two red points of intersection? Again, to find this, we set sine x equal to cosine x. And we ask ourselves the question, when does sine x equal cosine x? And so if you're not sure about this, it might help to get a unit circle going here. Right, and just start listing those common points, right? That first one is 1, 0. At pi over 4, the coordinate is root 3 over 2, 1/2. Sorry, that's pi over 6. At pi over 4, it's root 2 over 2, root 2 over 2, and so that right there should tell you, like, remember, sine is the y coordinate and cosine is the x coordinate. Notice how they're the same right there, right? So this first point of intersection over here occurs at, not root 2 over 2, but at the angle that produces root 2 over 2, which is pi over 4, right? That's the coordinate point that's down here, right? This is pi over 4. And then we have to find out, well, when does it happen again, right? So we should know it should happen at that over 4 one, right? Is it at 3 pi over 4? Well, no, because this one's negative root 2 over 2 and root 2 over 2. So those aren't the same, right? They're opposites. So how about down here? Well, this coordinate point is negative root 2 over 2, negative root 2 over 2, right? Because it's in the third quadrant where both signs are negative. So where does that happen, right? That's at pi over 4, 3 pi over 4, 5 pi over 4, right? So this is happening at an angle of 5 pi over 4. And so those are the limits, right? So we're going to integrate this from pi over 4 to 5 pi over 4. And so now we can actually do this integration because it didn't say we can use a calculator. The integral of sine is negative cosine, right? Because if I take the derivative of cosine, I should get negative sine. It's a positive sine. Minus the integral cosine is sine. and we're evaluating this from pi over 4 to 5 pi over 4. And so this is going to be negative cosine 5 pi over 4 minus sine 5 pi over 4. And then this whole thing, we're also subtracting negative cosine pi over 4 minus sine pi over 4. So cosine, we already talked about what these are, right? Negative cosine of 5 pi over 4 is negative root 2 over 2. So double negative here is going to give us root 2 over 2 minus, this one's also going to give us negative root 2 over 2, so it's going to turn this into positive root 2 over 2. In this case, negative cosine of pi over 4 is positive root 2 over 2 minus sine of pi over 4 is root 2 over 2. These ones are going to cancel, right? Those ones are going to go away, and we're going to be left with root 2 over 2 plus root 2 over 2. So it's kind of like 1 root 2 over 2 plus 1 root 2 over 2, which is going to equal 2 root 2's over 2, which equals simply the square root of 2. Right? So each one of these, the area of each one of these little regions is equal to the square root of 2 units squared. All right. Next example is a calculator-based one here that to show you what kind of skills you're required to do on your calculator. So go ahead and get your calculator out and clear out any of the mess that's in there now. They give us a graph here, and so we can start kind of setting this up. Maybe see if I can zoom in here. So we can start setting this up, and then just talk about where we get from there, right? So we want to do the integral of, I'm just going to go ahead and write it out, top minus bottom. And something to notice here, let me put some color on these, right? This is one function, right? This red outlined one is one function, and this blue one is another function. And so I want you to notice, like, well, the red one's not always on top, right? It's on top at first, but then it goes on bottom after 0, right? And then the blue one's on top at that point. Also, like, which one's which? Like, how can you determine which one's which, right? So, like, first of all, look at the blue one. What does that look like? And hopefully you're thinking it looks like an upside down parabola, which should indicate that it's the quadratic one, right? Because quadratics, the squared here means it's going to be a parabola, and then which leaves the red one to be the cubic. So because one of them's not always on top, we actually have to set up two separate integrals here, right? We're going to have to set up an integral for when f of x is on top and an integral for when g of x is on top. And because we're using our calculator, we don't need to write out like the whole function here because f of x is already defined. So we're going to start by doing f of x minus g of x. Right, and what this integral right here is going to give me, what this highlighted one here is going to give me, is this region there. Depending on, I need to set my limits of integration. So I think we can safely say that this should be 0. The upper limit should be 0 because they're intersecting here at 0, 0. But we're not really sure what this other point of intersection down here is, right? This is the one I'm writing down there. We don't know what that is, and that's what's going to go here. So let's go ahead and put these on our calculator and see what we get. So I'm going to type g of x first. Negative x squared plus 2x. And here we're going to have 3x to the third power minus x squared minus 10. X, if you don't have a calculator, graphing calculator, do it on Desmo. So you need to actually do this so you can see how it goes. Okay, we're going to graph this. And the thing to note is that the graphing calculator is going to do your first one first and your second one second. And so I'm getting this, which means, you can see my window's not properly set because
I can't see the point of intersection, that first point of intersection. So I need to be able to see farther down. So I'm going to say, let me try zoom fit. I've never actually used this before very often, but let's see what it does. Let's do zoom fit, which is zoom 0, and see what it does. Oh, that's absolutely terrible. So I'm going to go back to a normal window, and then I'll adjust it as we go. Oh, this window is actually better. So zoom 6 gave me a slightly better window, but I do want to see a little bit farther down, and I don't need to see all these. So I'm going to go from -5 to 5, and I need to see farther down, so I'm going to go to -15. And I think that's going to show me what I want. There we go. So what we're interested in is that first point of intersection, and we need to know how to use our calculator to do it. The most important things on the calculator to do are Math 8, Math 9 to calculate integrals and derivatives, and then second trace when you're looking at graphs, right? This screen right here is extremely important. You need to know how to do all of these things. Today we're looking at intersect, so that's number 5. It's just going to ask us first curve, second curve. What I want to make sure of is that it knows which point of intersection I'm trying to find, because there's 3 points of intersection. So I'm just going to put it over here. The first curve is g of x. I'm going to press enter. The second curve is this one, right? That's f of x. I'm going to press enter. And then it's going to say guess. And this is where it's really important to get as close as possible to the point of intersection. Doesn't have to be perfect. Press enter. And it's saying that it intersects at -2, x coordinate of -2, y coordinate of -8. Which that tells me that my lower limit here is -2, right? Which is nice. So this yellow region is going to tell me this yellow piece is going to tell me the area from -2 to 0. And then I have to add it to the region that starts at 0, right? And goes to here, which again, this looks like it's probably 2, but let's use our calculator to actually make sure it is. This third point of intersection over here. Let's go and go through those steps again. Second trace, intersect. So now let's just to be sure, let's go over towards the point of intersection we're trying to find, which is over here. Press enter. That's the first curve. Second curve is there. Press enter. Guess. Get it close. Press enter. And this point of intersection is 2, 0, which is what we hoped. But we don't check to make sure. So we're going from 0 to 2 on this one, and we want to do top minus bottom. So in this case, the blue function g of x is on top, and my f of x is on bottom. Right? So what this is going to tell me, what this piece is going to tell me is this region here. Right? And we have a calculator, so we're going to do this on our calculator, right? So let's go out to this where we calculate things, and we're trying to calculate integrals, so that's math 9. The first integral is from -2 to 0. And we're trying to calculate f of x minus g of x. So I do not need to type that whole thing in. I just have to remember, where did I put f of x? I put f of x as y2, so I'm going to press alpha, trace, go down to y2, enter, minus g of x, which was that's what I put in y1, like such, with respect to x, and we're going to add that to, we can do this all at the same time, math 9, the integral from 0 to 2 of g of x, which was y1, minus f of x, which was y2, dx, enter. And the calculator gives an area of exactly 24 units squared. Right? So sometimes you have to split it up into 2 separate integrals if they switch which one's on top and which one's on bottom. All right? So a little bit more to go. Okay, so let's look at example 6 real quick. And I want you to think about, like, with your current knowledge, how would you do this, right? And you're hopefully probably thinking like, oh, well, I just need to write the integral of top minus bottom. And so if you look at this one, like, look at this over here. Which function's on top there? It's the function that is on top of itself, right? And then over here, you can see that, well, now that, sideways parabola is on top of the other one, but, this first region over here is kind of funky. Like it's on top of itself. Does that mean I subtract it from itself? Doesn't that just mean I would get 0 area, right? And so that's why instead of doing area like vertically like we've always done, we're going to actually do area horizontally, right? So instead of drawing vertical little rectangles, we're going to draw horizontal rectangles like this, right? And this probably seems really confusing, but the only difference here is now the x coordinate is the height and the dy is the width of the rectangle, right? So it's not that bad. The only difference here is that we're going to have y's in our equation instead of x's in our equation. Okay, so if I'm trying to find area horizontally, then instead of doing top minus bottom, I'm going to do right function minus left function. And I'm going to put a little dy here, which means that y is the variable, right? Meaning all equations should be written in terms of y. And then the limits of integration are y coordinates, which is really important. You have to be putting y coordinates there, not x coordinates, right? So it's almost the exact same thing, except everything is getting replaced with y, right? So we're not doing top minus bottom, we're doing right minus left. So let's look at this and be like, okay, well, which one of these functions is on the right, right? We're trying to set up this integral. We're going to set up the integral. We're going to do right minus left dy. So this is going to be the function on the right is the line, right? Here is the line. I don't want to write, so it's tempting to write, oh, x minus 6. But don't write that because, again, because we're going in the y direction, we need to be using y's as our equation. What that means is we actually have to solve this equation. So it says x equals something about y. So we're going to add this 6 to both sides. And it's going to say x equals y plus 6. And this is the thing we're going to use, right? So that is the right function, y plus 6. Then we're going to subtract what's on the left, which this one's kind of nice. It's already in that form. It already says x equals y squared, so minus y squared dy. So please notice that everything here is in terms of y, right? It's all y's. There's no x's. And then we have to talk about, well, what should the limits of integration be, right? And that, again, that should be these 2 points here, right? It should be we need to find the points of intersection, right? So to find the points of intersection, we set the functions equal to each other. We know x equals y squared, so I'm going to take the second equation, y equals x minus 6, and instead of writing x, I'm going to write y squared, right? I'm replacing the x with the thing that x is equal to. We're going to get that. We're going to set it equal to 0, so subtract y on both sides. We're going to get y squared minus y minus 6. Factor. It's going to be y minus plus minus 3 plus 2. So the two answers here are when y equals 3 and when y equals negative 2. Right? So this y coordinate's negative 2. This y coordinate is 3. We could find the x coordinates too, right? So the x coordinate here would be 4, and the x coordinate here would be 9. What I'm doing is I'm using this equation, right? Plugging in the y, plug in 3, you get 9, plug in negative 2, you get 4. And so when we write these limits, we're going to go from negative 2 to 3. Please notice that we're using the y coordinates. We're not using 4 and 9. We're using the y coordinates here, right? Because all our numbers in here are y values. Okay, and then we integrate. So I guess we can just do this. Y to the 6 plus, not y to the 6th. Y squared over 2 plus 6y minus y to the 3rd over 3, evaluated from -2 to 3. And so if I plug in 3, we're going to get 9 halves plus 18 minus 9, right? Not 3 to the 3rd is 27. 27 divided by 3 is 9. Minus, plug in -2, we're going to get 2 minus 12 plus 8/3. And we do this. 18 minus 9 is 9. 9 plus 9 halves is going to be 27 halves. So this piece here is going to be 27 over 2. Minus 2 minus 12 is -10, which is -30/3 plus 8/3 is -22/3. So it's going to be plus 22/3. And then we have to add those together. So that would be 27 times 3 is 60, 81 over 6 plus 44 over 6, which is going to give us 5. When you add those, you get 125 over 6, I believe, right? Let me just check on the calculator, but I won't do it while the videos go. Actually, this is a good opportunity to show you how you would do this in the calculator, right? Because the calculator is not going to let you put in, it's not going to let you put in y values, right? So like, what do I actually put into my calculator? Well, because it doesn't let you put in y values, you can still just put in x values, right? So we're just going to go ahead and type the same thing we see up there, except we're going to be putting x's instead of y's, and it will give the same, it should give the same answer. It's just like there's no way to put a y in there, and it doesn't really matter. That's 20.33 whatever, and what 125 divided by 6 is the same thing, right? So we got the correct answer. Okay, last one. We want to find the area of the region enclosed by y equals the cube root of x plus 1. Y equals the square root of -x plus 3, and y equals 0. This is a calculator problem, right? So if it didn't say it here, but this is calculator allowed. The first thing I want to do is I do want to sketch a graph because I want to see what this looks like. So let's go to our graphing calculator and let's have it help us sketch a graph. If you don't know how to put in a cube root, you got to go to math and then down to number 4. So cube root of x plus 1, and the other one is the square root, which is a second that, -x plus 3. We're going to graph these, and we're probably going to have to change our window here because they're not going to be, yeah, I think I entered something wrong. Okay, I guess it's good. So I don't like my window. I'm going to go -2, and I don't need to see this many of these guys. So let's see how that goes. Okay, so that's the cube root function, and this is the square root function. Okay, so we are interested in that region there. So let's sketch these real quick, and let's give them some color. So let's call this one red, let's call this one blue. The cube root one looks something like that, and the square root one looks something like that. And we're interested in, oh, and then y equals 0. If you don't know what y equals 0 is, that's just the, we'll do a third one. We'll do that in, I'll do that in yellow. That's just y equals 0 is just the x-axis, right? So it's just down there. And we want this green region, right? This is the area we're trying to find. So what I want to point out here is you could do this in several ways, right? You could do 2 separate intervals, right? Like notice there's 2 regions here. There's this one here. Let me do it this, like there's this one over here, and then there's this one on the right. So I could set up the integral for the first one, and then add it to the integral of the second one. What we would need to know for that is this point of intersection. So let's use our calculator to find that. Again, second trace intersect. First curve, enter. Second curve, enter. Guess, get close, press enter. That point of intersection is, I'm going to need some more space. And we need at least 3 decimal places here. You really don't want to round in the beginning either, because then you lose some accuracy. 1.2718368, comma 1.3145962. I'm just going to write them all out because I want to be very precise with this. I don't want to lose any information. So let's do it. We're going to do this 2 different ways. The first way is we're going to integrate from, you know what, we need to know this point of intersection as well, right? Where does it cross that axis? So that we can find on the calculator as well. We want to find, in this case it's actually a 0 because it's when it's crossing the x-axis, so we're going to say 0. It's going to ask when is it left bound, so we're going to go to the left of the 0 we're trying to find. Right bound, go to the right of the 0 we're trying to find. Guess, we get close, and it's at -1. Okay, so that's good. It's at -1, 0. So to find region 1, I'm going to write this in. This is region 1. We're going to integrate from -1 to 1.2718 ... and what are we integrating? We're integrating the red curve, which is the cube root of x plus 1. That'll tell me the area of region 1. And then we're going to add that to the other region, which starts at 1.2718 whatever, until here, which that's 3. And what are we integrating there? We're integrating the blue function, because that's the piece that's above the x-axis. And if we integrate this, let's go ahead and do it. Let's just remember what we put that. Okay, the cube root's on top, so we're going to do math 9, integrate from -1 to 1.2718368 of y1, and then we're going to add that to the integral from 1.2718368 to 3 of y2. And since our functions are in terms of x, they're both the x, and we're going to get the area is, it's taking it a little while, 3.75. When you do the final answer, you only need 3 decimal places, right? When you do the final answer. So there's one way of doing it. Let me show you another way of doing it. Let me erase some of this stuff so it's not so messy up here. Okay, another way of doing this would be to, we're still trying to find this green area, but instead of doing 2 separate integrals, we can just do it horizontally, right? Notice the blue function is always right of the red function. So let's write over here, we're going to do a separate method, right? So method 2 is we're going to write an integral of the right function minus the left function dy, because we're doing it in the y direction, right? What this dy means is I need to solve all these in terms of y, right? First thing to recognize is the right function is the blue function, right? So this is the one that's on the right. It's y equals square root of -x plus 3. But again, I can't put x's in there. I need to put y's in there. So we're going to solve this, right? We're going to square both sides. We're going to get y squared equals -x plus 3. We're going to subtract 3 on both sides. And then we're going to divide by -1, which is going to give us, right? And that's what we're going to put for that first piece, right? Negative y to the third plus 3. And then we're going to do minus the left piece. The left piece is the red one, which is y equals the cube root of x plus 1, which again, we need y. We need x equals a bunch of y's because we need to put y's down there. So we're going to solve this. We cube both sides to get rid of the cube root. We subtract 1 and we get y cubed minus 1 equals x. And that's what goes right here. And then this whole thing dy. And I messed up on something down here. I, for some reason, changed this blue function to y cubed when it should be y squared the entire time, right? Then we need to know what are the limits of integration. Remember, we're using y coordinates, so bottom, top, what's the lowest y gets? Well, the lowest y gets is here on the x-axis, which is a y coordinate of 0, and the highest y gets is the y coordinate up here, right? That's the point of intersection for them. So the y coordinate here would be 1.3145962, right? And so we can integrate that. Again, we can do it on the calculator. We're going to do math 9. We're going to integrate from 0 to 1.3145962 of what? Well, I can't use y1 and y2 because those are different things, but we can just put these in. Negative x squared plus 3 minus, let's just go and distribute that thing in there. It's going to be x to the third, negative x to the third plus 1 because the negative distributes, dx. And again, I know you're probably like weirded out because I'm putting x's in the calculator when it says y's, but it will give the same thing. It will give the same answer, and it should match our other answer as well. It gave it a lot faster, right, than the other one did, and you get 3.754, which is the exact same answer in a completely different way. And one of them might be easier for you than the other, but you need to know how to do both. All right, so that's all that there is for this. In class, we'll go and practice this stuff.